Good morning. Today we're going to be going through section 11.1. It's about the flow of energy. This relates to unit 11, which is over thermochemistry. The pages that these notes are going to be found on is from page 292 to 299. I'm just going to kind of debrief what happened in this section. So, and I'll try to go as quick as I can with this. So, thermochemistry. What that means is we're talking about changes in heat during a chemical reaction. That could be heat gained or heat lost. Okay. And then just some vocab words. Talk about work. Work is the force needed to move an object. Energy is the capacity to do work. And then we have what we call chemical potential energy, which is the energy that's stored within the structural units, the atoms themselves, in a substance. So it's the energy stored within the structural units of a substance. All right, so then we want to move and talk about heat and that relationship between energy and heat. Heat will be represented by the variable Q for us. Lowercase q, uppercase q, doesn't really matter. So heat is defined as the energy that gets transferred from one object to another, and that's due to a difference in temperature between the two objects. So we all know that things go from hot to not, warm to cold, things that from a higher temperature always to a lower temperature. That's always going to be the direction of energy transfer, heat transfer. So heat, again, we're going to represent as Q. That's the energy that gets transferred from one object to another. Due to a temperature difference. Things will flow, again, from hot to cold or hot to not. All right, and then very important, when we look at a system, something that's gaining or losing heat, we always want to look at it from the perspective of the system. So the system is going to be what you focus your attention on. The surroundings are going to be everything else, or the universe, or what we call the universe. So the system is the part on which you focus your attention. And the surroundings is going to be everything else. And sometimes we refer to that as the universe. So very important when we look at these chemical reactions and we're trying to determine if heat has been gained or lost, or if it's an exothermic or endothermic reaction, we always have to take our perspective and put it in place of the system, because it's all relative to where your perspective is. So always have that perspective from the system. All right, And then the law of conservation of energy is another thing this section talked about. It's very similar to the law of conservation of mass, matter. Energy can't be created nor destroyed. It's going to be either used as work, supplied as heat, or it will be stored. Okay, so we'll say energy is neither created nor destroyed. It's going to be either stored, used as work, or supplied as heat. And again, direction of flow is always given from the perspective of the system's point of view. We'll say direction of heat flow. So it's given from the point of view of the system. If we have heat flowing into the system, our Q or our heat, Q is always going to be positive. If we have heat flowing out of the system, our Q is always going to be negative. So heat flowing into system, Q is going to be positive. And if we have heat flowing out of the system, our Q will be negative. Okay, and again, this would be our exo and endothermic reactions, which we'll talk about here in a second. Just a couple more things for 11.1. All right, so an endothermic reaction, I know you're familiar with this terminology, just may not use it too much, so we may have forgotten it. Endothermic, endo means to enter, so that means the system is absorbing heat from their surroundings. And then our exothermic, thermo means heat, endo to enter, exo to exit, to leave. That means that we are releasing, so it releases heat to the surroundings. Our SI unit that we will use for heat is going to be the joule, and that is represented with an uppercase J. It's our SI unit for heat and energy. And one other thing this unit talked about, or this section talked about, was specific heat. Specific heat is how much heat can a substance or something absorb before that substance itself heats up. And we really use the specific heat of water. That's represented with like a large C, capital C, for a variable. And that's defined by the amount of heat it takes to raise the temperature of that substance, raise it 1 degree Celsius, 1 gram of that substance. So how much heat does it take to raise that substance, 1 gram of that substance, 1 degree Celsius? That's our definition of specific heat. And again, it's how much heat can something absorb before it actually heats up itself. Water has a really low specific heat. It can absorb a lot of heat before it heats up itself. So we use water for a lot of different things. Specific heat of water is why the coast, cities on the coast have moderate climates. And it's also why you'll see citrus farmers, when it's going to freeze, they'll spray their farms. I think you read about that, because it's absorbs that heat and then releases it and it protects the crops. So, but again, specific heat is the amount of heat it takes to raise the temperature of 1 gram of the substance 1 degree Celsius. And the formula we use for specific heat is C equals Q, which is our heat, over our mass times delta T. Delta T, reminder, delta T is our change in temperature. Delta is our change in temperature is always going to be final minus initial. So that's that right there for you. And our units for specific heat are going to be joules. So if we just look at this, Q units are, Q is going to be in joules over grams, which is our mass, times degrees Celsius. So right here is your unit that you're going to use for specific heat. It's joule over gram times degrees Celsius. I will work through a sample problem here in the next video.